Believe it or not, Falcons, we are into chapter 16, and this is our first foray into random variables. So as always, look over these homework problems. This is a little bit not complex, but more just you really need to stay organized with your thinking here. And I think these problems illustrate what you'll need to be able to do to be successful with dealing with these probability tables and expected values and variance. And it should flow through this objective of students will know the definition of expected value of a random variable and describe the effects of shifting and scaling on that expected value. And you hear this term expected value, and you hear this term a random variable. And all we're saying is a random variable takes a value based on the outcome of a random event. So what we say is we use a capital letter like x to denote the random variable. So we say some variable x. And then the particular value that we're looking for of that random variable, it's often denoted with a corresponding lowercase letter. So it's like the probability of x, which is our model, is equal to some value x. And that first notation is a little confusing because we'd often indicate, especially with probabilities, like what's the probability in our model that we randomly get this event to happen. So there are two types of random variables that we will be encountering for the rest of the year. One are discrete random variables, and discrete, the best way I can say is they are countable, or they can take on one of a countable number of distinct events. So think like credit hours or test scores on your last test, versus a continuous random variable can take on any numeric value within a range of values. So for the example, like a cost of the AP exam this term, it could take on any of those values. Versus your test, there's really just whole points or maybe half points, but otherwise that's it. You can't get a pi as an answer or as a number of points on your last test. And so when we talk about random variables and we're talking about modeling, we go back to our first principles and we talk about the center. So the probability model for a random variable consists of a collection of possible values of the random variable and the probabilities that the values occur. So if we have 2 or 3 events, each one of those is not necessarily equally likely. And that's our first foray into the probability tables that we're going to do. So of particular interest is the value we expect a random variable to take, which is notated as mu for our population mean, or E of x, with x being our random variable for expected value. In either of these cases, we are talking about means. We're talking about the center of a distribution. We've been doing that work way back in semester 1. So here's the new notation. An expected value of a discrete random variable is the sum of the products of each possible value with the probability that it occurs. And do note, be sure that every possible outcome is included in the sum and verify that you have a valid probability model. So when we say a valid probability model, we're saying that all of the probabilities have to add up to 100. For example, a player pays $5 and draws a card from a deck. So you are already down $5. If she draws the ace of hearts, she wins $100. It's pretty good. For any other ace, she wins $10. For any other heart, she wins $5. She gets her money back. If she draws anything else, she loses. So the questions I would have for you guys, if you were all in front of me right now, is, would you be willing to play the game? Why or why not? What price would you pay to play this game? Is $5 a good enough amount? Is the payout what you want it to be? Then the third question would be, would you be willing to pay to play if the top prize was $200? And so let's get into those questions. And let's reset up this model. So again, you're paying $5. Draw a card. If it's the ace of hearts, you win $100. Now note, you paid $5, and if you draw the ace of hearts, you get $100. So you net $95. That is the outcome you would get. And there's only one chance that happening. There's 1 out of 52 to get the ace of hearts. For any other ace, you win $10. You pay 5, you win 10. That means you're up 5. And there's 3 out of 52 aces left in the deck. If there's a heart, which is not 13, but 12 chances, because we already considered the ace of hearts, note some conditional, so that's 12 out of 52, you get your $5 back. So you net 0. And then if you get anything else, which is 36 out of 52, you lose $5. So we can come up with this probability distribution. This is our model. We have our variable, which is winning the game, and your payout. So if you draw an ace of hearts, you win $95, but that's a 1 in 52 shot. So if I take this distribution, what I want us to do is find the expected value, which is the mean. So just like with anything with means, we add them all up and we divide by the total number. Well, in this case, the total number is 52. And so if you think there's 1 chance of drawing ace of hearts, and there's 3 chances of drawing the other 3 aces, and there's 12 other hearts to draw, and there's 36 other cards. Well, if we look at it as a probability, what we would do to find the expected value would be 95 times 1 over 52, plus 5 times 3 out of 52, plus 0 times 12 out of 52. That's a pretty easy one. Plus negative 5 times 36 out of 52. And what we're doing is we are finding the mean or the expected value. What would you expect to get paid if you played this game over and over and over again? And by taking those values, I see that this game is rigged against me. It's not a fair game. So our mu, our mean, our expected value, is each of those outcomes. In this case, what is our payout times the probability that it happens. And we add them all up. So losing $1.35 every time is not the best deal. So the second question that I asked you was, would you play this game if the payout was 200? And you're like, well, it's only 1 out of 52. Why would that change my expected value? And this is where game theory comes into play, which some people have seen before. But if I change the payout from 100 to 200, then the only thing that's changing is the payout for the ace of hearts. It's now $195. And if I take that accounted into my expected value, I now get a positive payout. So I have 195 times 1 out of 52 plus the same other values. And I get around 0.57. This is positive, which should mean you should play. Because in the long run, you're guaranteed to make money. Versus the other game, in the long run, you're guaranteed to lose money. So this is the first idea on expected value, and it focuses on the center of things. Well, what do we always talk about? Shape, outliers, center, and spread. What's the next thing we should talk about is the spread. So for data, we calculated the standard deviation by first computing the deviations from the mean and then squaring, and then we took that, we divided by something, I think it was n minus 1, then took the square root. We do that with discrete random variables as well. So the first thing that we find is called the variance. The variance, or sigma squared. This is the Greek letter sigma, Again, we use Greek letters to talk about population. So the population spread, or the variance, is each of the values minus the mean squared times the probability. Get used to this formula. It's a great one. So then how do we go from variance to standard deviation? Well, we simply square root it. So the standard deviation, or sigma, is the square root of the variance, or the square root of the difference, the sum of the difference of the value minus the mean squared times the probability. So what was the variance, or the spread, of the scores that we had in our card game? What is the variance of the distribution of winning in our gambles? So let's go back to the $100 payout version. What do we mean by each of these? So we knew that the mean was negative 1.35. Let's just write that up there, negative 1.35. We're going to take each of these values, let's say in green. We'll do 95 minus negative 1.35 squared times the probability. Then we'll do 5 minus negative 1.35. Then we'll do 0 minus negative 1.35, square it, times the probability. So the first one, 95 minus negative 1.35 squared, times the probability, plus 5 minus negative 1.35, whole thing squared, times the probability. 0, negative 5 minus negative 1.35 squared, times the probability. And each time we do that, to find the standard deviation, we simply take the square root. So 190.4955 is our variance. How far away from the expected value, or the spread, is. And the standard deviation is how far away from the mean. So standard deviation, or sigma, or S sub x, if we were talking about data values that we talked before, 13.8. This is dollars. This is how far away we are from that mean. And what's pushing it high is that high payout of $100. It's going to shift our spread a little higher. So more about means, and then we'll call it here. Our second video will only be on this one compound problem that's utilizing what we talk about here. And then we'll wrap up with 2 problems in part 3. This is really just a lot of examples going over expected value and variance and their basic properties. So remember with means, we're talking about the distribution generally of a normal model. So if I draw, or poorly draw, a normal model, and if I add or subtract some sort of number to my distribution, all I'm doing is shifting that bell curve left or right. So adding or subtracting a constant from the data shifts the mean, but does not change the variance or standard deviation. Now, why is that? If I'm just adding or subtracting to every value, the spread is staying the same. Doesn't matter where this is located. I'm moving the mean, so the mean's going to change by some added value or subtracted value, but the variance stays the same. Consider, for example, everyone in a company receiving a $5,000 increase in a salary. That would be amazing. The mean salary would also increase by 500, but the variability, which is the spread, because everyone got that shift, there's no change in the difference between the highest paid and the lowest paid. When it comes to multiplying by specific values, this is what affects both, and it doesn't affect it in the way you think. So multiplying each value of a random variable by a constant multiple multiplies the mean by that constant, and the variance by the square of the constant. Well, as we've seen with expected value, if I'm scaling it, if I'm growing it larger, then if I put it into my formula, it would just be a times whatever value times p of x. Everybody gets that multiple, And so all this is just a factor of a outside, which is why we can say that e of some sort of constant multiple is just that multiple times the expected value. And I know this seems theoretical. We will do plenty of examples for you to see where this comes from. But let's do the same thing with the variance. I argue that if you multiply the random variable by some sort of constant, then we multiply by the square. Well, let's follow through. If we plugged this in to our formula, here I have ax minus a mu squared. Well, both of those are squared. So then I can bring out a square term here, which means I can bring out a square term here. And this formula right here is just my variance of x. So that simple algebra of pulling out that square term shows me that if I'm multiplying by a constant, it's the variance squared. And the example that goes with this is, consider everyone in a company receiving a 10% increase in salary. Each salary would increase by 10%, but also the variability, the skewness, would increase by 0.01. For the people making a lot of money, they're not shifted. People making a lot of money, or little money, are drastically increased in comparison to their spot. Think variance is about our spread. So, in general, the mean of the sum or difference of the distributions of two random variables, maybe not one, but two, is the sum of the means. So it would just be, if you have like x plus y or x minus y, then we just add them or subtract the expected values. If the random variables are independent, and we know what they mean, that means one does not depend on the other or one's not influenced by the other, the variance of their sum or difference, it doesn't matter if you're adding or subtracting, their sum or difference is the sum of the variance. The reason why we need both independence and variance is always the sum. Notice, not standard deviation, not sigma. We're not talking about standard deviation here that we add. We add the variances. Now, I've heard this referred to as the Pythagorean theorem of statistics, and it stuck with me, and I wanted to share that with you. Variances, since they're squared, we add them before we take the square root. So variances add only when the variables are independent. And that's why we made such a big deal about independence. So last example, last two slides really, and then we'll call this video. So let's say you mix a quart of lemonade. There should be 32 fluid ounces, but your measuring process isn't perfectly accurate. 32 ounces is the expected amount, but there is some variability, right? And now take that pitcher of lemonade and pour a 12-ounce glass. Now that measurement isn't perfect either, so the expected value is 12 ounces, give or take a little, right? There's a little fluctuation. How much is left in the pitcher? Now, you should think it should be around 20 ounces. That is the expected value with the subtraction. But given the uncertainty about the initial amount and the variability in how far you filled the glass, you can't say exactly how much is left. In fact, there was a little give or take with the first setup, and then a little give or take with the second pour. So there is less certainty about the amount left because you removed an unknown amount. So subtracting some lemonade has increased the variability in the amount remaining. Hence, variances add. Keep saying that until it sticks. Variances add. Now, with continuous random variables, or values that you can take on everywhere, random variables that can take on any value in a range are called continuous random variables. Obviously, that is problematic when considering what we have done to this point. We cannot list out all of the values of the variable with the attendant probabilities. Our tables don't match, especially for the card game. If we have only a single value, there can be no probability. However, the distribution of a continuous random variable does have a mean and a variance. We will not concern ourselves about how to calculate these means and variances in this class. That was why you took this class instead of calculus, okay? How do you divide an infinite sum by an infinite value? But we'll work with the models for continuous random variables when we have appropriate conditions and parameters. So that puts us at a good spot to pause here. I really want you to wrestle with expected value and variance in the next 2 sets of videos. We're going to work through the Johnstone's Jeep Junkets and Becerra's Bronco Buster problem. If you want to get your calculator set up for this, that would be great. This is going to be an interactive video lesson, so I need you to be ready to go in the next one. So, thank you for your attention. I will see you later, Falcons.